Okay, so Dr. Pingle here. We're going to talk a little bit about one of the notebook pieces, and that is to work with some elevation data to work on slope shading. So in this case, I'm at the SRTM tile grabber. I'm just going to grab one of these tiles off the coast of California. You're welcome to grab whatever it is that you're interested in. So I'm downloading SRTM 1205. This is a 90 meter elevation data set. It doesn't really matter what your spacing is, so pick whatever you're interested in. I'll pause the video here while this finishes the download. Okay, that data's come in, and so I just want to unzip this. So we're going to extract that here. So here's my data set. And I can bring this directly into ARC. So I'm going to copy this path name here. It's going to make life a little bit easier. Here I've got a just a blank project, and I'm going to add this data in. And you can just browse to wherever you saved it, or you could paste this path up here, whatever you'd like to do here. So there's that SRTM data. You'll see it show up over here on top of California. Okay, here it is. So this is an area right by the San Francisco Bay. So it's brought this in as a default color map here. So it goes from white being the highest elevations at 990 meters and -40 being the lowest. Since we're going to be working with slope shading, we want to make a slope raster. So the easiest way to get started with that is to go to your tool set. So you can go to Analysis and choose Tools. And the very first thing that I actually want to do is I'm going to project this raster. So I'm going to type in project raster and project this into a local coordinate system. Now there are ways around that, and you don't necessarily have to do that, although I strongly recommend it. If you look up UTM zones, the area that we're working in here, this is kind of my go-to image. The area that we're working with here is on the west coast of the United States. So it's right here in zone 10. So we're going to reproject our data into UTM zone 10. So our input raster is going to be the one we just unpacked. You can put this wherever you want. I recommend that you sort of keep track of everything. By default, it's going to drop everything into this geodatabase associated with your project. So that's probably fine. The output coordinate system, I want to use UTM zone 10. So I'm going to choose, we have these two divisions here between geographic and projected. So geographic would be another latitude and longitude based system. But I'm going to use projected UTM. There are a lot of different variants of UTM, which a lot of people don't realize. I'm just going to reproject into WGS 84, but in a UTM coordinate system. And then I'll change this to UTM zone 10 north. The resampling technique is actually pretty important. Nearest neighbor is almost never a good idea. So you want to change this to one of these two. You can do a little looking up online to look at the differences. Bilinear is going to just use 4 of the nearest neighbors, and then cubic convolution is likely to use, I think, 16 of the nearest neighbors to make a judgment. So this will control sort of how smooth it looks. I usually use cubic if I've got the time. The output cell size, by default, it's going to calculate this for you. It's going to be based on the latitude of where you are. You can see that we're hovering right around that nominal 90 meter resolution. So you don't need to necessarily change this, but you could if you wanted to. So we'll just hit OK or run. So this will just take a minute to reproject. I'll pause the video and we'll pick it back up again when it's done. Okay, that projected raster is done. So that's right here. You can see that it actually looks fairly similar to what we had before. The differences are really related to a better estimation of what the statistics are here. So you can see that now the range goes all the way up to 3,129. So that's likely due to just a recalculation of the statistics and not a change in the underlying data. But it wouldn't hurt to double check that and make sure that things didn't go too far out of whack. If you did want to check that, you could do things like use an identify tool to take a look at that. Okay, so the next step is to calculate the slope. So we want to go back and use a different tool this time. So this time we're just going to use the slope tool. This can be found in both of these toolboxes. It works the same no matter which one you choose. The input raster then is just going to be the projected raster that you made. This is the output raster, again, being written to the project's default geodatabase. Now the output measurement, you do want to pay attention to this. This is set to degrees. That's probably what you want to use here. But an option is %rise. And then the method that you're going to want to use, you can either use planar or geodesic. If you have the time, it's usually better to use geodesic. As long as you're working within kind of a local coordinate system again, planar should give you pretty reasonable results. Now this z factor is an expression of the relationship between the angular measurement and the vertical measurement. So in this case, once you've done the reprojection into UTM, both the vertical and the horizontal are in meters, and so the z factor is 1. There's a 1-to-1 relationship between the meters and the vertical elevation and the meters and the horizontal elevation, or horizontal change. But if you're working with the original here, that's not true. So if we were to use this raster to do the input, we would want to set this z factor to something else. Now you can calculate these. There's some information about that in lecture, and you can Google these. But you would absolutely need to make sure that z factor was set correctly. Usually it's going to be a very small number. 0.0001 or something in that ballpark. So this is why you really want to project your raster first. Okay, so one of the things that's going to make your life a little bit easier is to change this. So instead of writing it out to your default geodatabase, write this out as a geotiff file. So we're going to call this California slope.tiff. I'm going to leave these to degree and planar, and we're going to leave the z factor at 1. So we're going to go ahead and write that out. That's going to get you to a very similar rendering of slope that we saw in lecture. So by default, this is going to be a classified system. And if you take a look at these, you can go ahead and include these in the notebook. This is a pretty nice rendering of slope. It's pretty easy to see the steep slopes, so you get some steep stuff in here, and the shallow slopes. And so we have this convention that darker is steeper, which is what we want, but it's a nice sequential color scheme, so not a lot of extra color that we don't need. We're going to play around with this a little bit, though. Before we do, if we zoom in on this, one of the things we talked about in lecture was turning the display so that this is going to be a little bit smoother. So you'll want to know where this is a little bit later on. If we go to raster layer and appearance, we can change the resampling type to either of these two. Now these are just for display, so in this case I'll often just choose bilinear, but you can see that it smooths this out quite a bit. If you find that you don't like how that looks, you can do cubic, and of course you can always use nearest neighbor, which is essentially going to be the pixelated version. And at a certain view scale, that should look just fine. But if you find that it doesn't, you may want to change those. Okay, so the next portion here, we'll change that back to bilinear. We're gonna work on some of the slope shading that we talked about in lecture. So the first was just sort of a mimicking of Lehmann's system, which is to say a linear scaling from 0 to 45 degrees and then black after that. So we're just going to right click on this. We're going to go up here and look at the symbology. So here you can see that this is set to classify. We're going to change that to stretch. We've got a color scheme that now goes from black to white. We can reverse that very easily by clicking on this and choosing Format Color Scheme and clicking on the Reverse Color Scheme. So now we've got something that goes from white to dark. Again, the idea is the steeper the darker, which is our common convention. We've got other sort of familiar ways of managing this. Right now it's set to % clip. We could change that to minimum and maximum. We can change the statistics that it's getting from the data set, or we can define some custom ones, which is what we're going to do. So we're going to define this as a custom. So right now it goes from 0 to 57, now 57.54. Now, there's nothing particularly wrong about that, except for that that's just going to really depend on what the maximum slope is. So in this case, the maximum slope in this raster that we have, I'm just going to turn that off because it looks a little bit awkward. The maximum slope we have is about 57 degrees. So you want to make sure that this is set to something consistent. You could set it, for instance, to 90, which is going to have the effect of lightening it out. Now, from this perspective, the 0 maps here. This is actually just a bug in the software. It did change, as you could see. And then 90 is set to black, so it goes from 0 to 90. But what we want to do is we want to set the blackest part here to 45. So we just change this value to 45, and that's going to have the effect of darkening that up, bringing out some of the contrast. So that in effect is the Leman system. Now the next one was vertical exaggeration. Now vertical exaggeration is essentially going to be applying, multiplying the vertical effect of your original elevation raster by a given scaling factor. So we could, for instance, go into analysis and look at a tool, and we could use the raster calculator, and we can apply. Essentially, we're going to take our projected raster. We're going to multiply that by a given vertical exaggeration. So in class, I had said that anywhere between 2 and 3 is usually a pretty good value. I'm kind of partial to this 2.3, which is one of the results I found through some empirical experimentation. And I'm just going to write this stuff out again. You can write it out wherever, but I have seen that it works a little bit better if you write it out as a geotiff. We're going to call this slope VE for vertical exaggeration.tiff and run it. And actually, this is a misnomer. That shouldn't have been slope, because what we're really getting is an elevation value. But now what we can do, so these values are elevations. So for instance, if we click on our map and we just click on a given point here, our stretched pixel value for our, and again, this is elevation, is 388. Let's see if we can pick somewhere kind of consistent. So that's 29.9. If we take our original one and we clicked on that, what we'd find is that's a lot lower. So that's 14. So essentially what we've done is we've multiplied this original surface by 2.3. So if we were at somewhere that was 10 meters of elevation, now we're at a 23 meters of elevation. Just a 2.3 scaling factor. So the next thing that we're going to do here to calculate the slope is just again run the slope tool on the feature layer that we just had. So we're going to take this, we're going to write it out again. This can all be kept intact and we can run it. Okay, so we're going to get this classified slope again, so we can go back and look at the appearance and change the symbology. We're again going to change this from classify to stretch. We're going to invert our color scheme just like we did before, so the steeper the darker. And you can see that already we've got quite a bit more contrast going on here. We can go up into resampling type and change this to bilinear to kind of smooth that out again. So if we set this again to minimum maximum, and we set the statistics again to custom, which we can then define down below, we can make that go from 0 to 90. The difference here is that instead of going from 0 to a real 90, we've exaggerated these slopes. So we've scaled the elevation, and then we've calculated slope off of this exaggerated surface. So if we wanted to compare these two, this was our original one, scaled via the Lehman system. This is our new one. We see that we've got some similarities here. This one is a little bit even. The Lehman system has some very, very dark values in here. Now, if that's what you're looking for, that's great. I think that the softer one is a little bit nicer, but both of these are perfectly good. Now, there's actually a way to calculate this a little bit more easily. So if this was our original elevation surface, and we wanted to do a calculation here, hopefully we didn't just crash ARC. So if we go back to our tool set here and run slope again, there's a shortcut to doing that vertical exaggeration. So if we take our original one and we write this out as real slope ve2.tiff. This z factor, again, the idea was it controls the relationship between the vertical units and the horizontal units. So if we want to apply a vertical exaggeration, it's actually easiest, instead of going through and using the raster calculator, we can actually just apply a z factor straight out. So we can say z factor is 2.3. That's going to apply a vertical exaggeration of 2.3. And so if we go back through and we apply the same settings as we had before, so we change it to stretch, we change it to maximum minimum, we reverse this so that it's the lighter the flatter, the darker the steeper, and then we change this to custom. All right, so we've basically just gone back through and we've set this one to exactly what we had it for the other one. You can see that there's no difference between these two, right? So this second one we calculated just through the z factor. This first one we used project raster. We used the raster calculator and then applied, and you can see that there's absolutely no difference between those two. Okay, so to simplify this a little bit, we really don't need two of these, so I'm going to remove the first one actually. So we could just turn it off, but I just want to get it out of here. This one was improperly named. That was the vertically exaggerated elevation surface. This was our Lehman surface, so I'm going to just rename that. Okay. So the next two are vertical illumination and sign shading. So let's start with vertical illumination. So if we wanted to go to analysis, we could apply the tools. And vertical illumination is nothing more than a hillshade. So this one you can put anywhere you want. But the only difference here is that instead of the altitude being at 45 degrees, we're going to make this at 90 degrees, which means the sun is coming from directly overhead. So it's 90 degrees off of the horizon. So if we run that, what will happen is we'll get a surface with relatively poor shadowing that looks something like this. So you can see that in contrast to what we've already seen, this is quite a bit whiter. So this is essentially a cosine model, and it has the effect of making only relatively steep slopes dark. Everything else kind of gets this white look to it. So we could just rename that vertical illumination, and that can go right in your notebook. Now the last one is using the sine of the slope to calculate the value. So in this case, this surface is a slope surface that's just been symbolized in a way that's consistent with Lehman. And so we can actually use the raster calculator on that slope surface. Oops. All right, so we're going to essentially take our Lyman surface, which is really just a slope. We need to convert to radians, so that's going to be pi divided by 180. So we're just going to approximate pi 3.14159 divided by 180. What that's going to do is that's going to convert our degrees into radians. The reason we need to do that is because we need to apply the sine. But the sine function only works on radians. It doesn't work on degrees. So if you don't do this conversion, you're going to get something a little bit strange. And then we're just going to call this something else. We'll call it sine and hit OK. So what we're going to be getting out of this is a scaling of the degrees from 0 to 1. So you can see our maximum value here is actually 0.84, but with a slope of 90 degrees, we would have had 1 as our maximum value here. So we're just going to go into the appearance, and we're going to change this. We're just going to invert this color scheme, just like we've done before, the steeper the darker. This already looks pretty good, but again, we want to be consistent about how the stuff is rendered. So instead of having it go from 0 to 0.84, we're going to do exactly what we did before and change that to the theoretical minimum and maximum. So we'll change this to custom and then change that to 1. And that's going to have the effect of just sort of lightening that up just a little bit. This is the sine-based shading, the Miller and Summerson vertical illumination, which is really just a hill shade at 90 degrees. Vertical exaggeration, where you can either use the raster calculator and then apply the slope, or you can just use a z factor of something between 2 and 3. And then just our standard slope, just scaled from 0 to 45. So what I'd like you to do is go through there we go. What I'd like you to do is just go through and compare these and see what you think. The vertical illumination is obviously the most different, but how does sine differ from vertical exaggeration? Which one do you like better? Which one do you think provides an overall more pleasing appearance? Same thing with sine versus Lyman. You can do a direct comparison and sort of see which of these you like. One of the tools that's kind of useful for making direct comparisons is the swipe tool. So rather than turning a whole layer on and off, you can peel them back. So this is the sine layer. You can kind of peek under that, and then it's going to go down to the next lowest layer. So that's Lyman. So sine and Lyman. So it kind of lets you make a nice, more direct comparison. So you can do that if you want for the notebook as well. Hopefully that gets you going on this section of the notebook. Definitely email me if you have any questions, and good luck on the notebook. Thanks.